In this lecture, we're going to do our first structural mechanics problem. We're going to do a plane stress problem, and we're going to investigate different solver techniques, implicit and explicit techniques to solving this, as well as we're going to talk about a few of the things to think about when doing stress analysis. So, as I mentioned, we're going to get a problem out of a book from Thomas Hughes and his co-authors Austin Cottrell. So the book is Isogeometric Analysis Toward Integration of CAD and FEA, and you can get this through the BYU library, and you can get a digital copy if you click through once you're signed in, and it's found on page 116, section 4.2, infinite plate with circular hole. And so it starts here, and note that there are analytic equations. These are repeated in the homework assignment. If you want to find the full problem, you can actually find the reference here from Gould in 1999. And so then this is the geometry. So it's an infinite plate, but with standard finite elements, we're going to have to model this as a finite plate. And so just note that the dimensions, the outer dimensions here are going to be 4. Okay. And I do recommend that you read through, especially this first paragraph is going to provide some of the insight that we're going to talk about in the homework assignment. And so I actually kind of recommend reading through the whole thing, as well as when we look at our mesh refinement. I would recommend maybe trying to copy the meshes that are created here, at least as many as you can do with a student edition. And then you can compare your results and look at, say, convergence rates provided here. A note to mention here is that this book is called Isogeometric Analysis, and they're using a C1 NURBS basis function. And that's kind of a key point to contrast against in your homework assignment. Okay, so let's get started. Let's start by opening up Abacus. Okay, now Abacus is open, so let's go ahead and create our standard model. We're going to create a part, and we'll call this a finite plate. Now in the modeling space, we're going to be in 2D planar. Our base feature will be a shell. As you recall, our outer length was around 4, and so I recommend just at least scaling this down to say 20 for the approximate size. Now, also a key point that I'll mention is notice that he's defined X direction here going to the left. And so just so that we keep consistency on our dimensions, we're going to do that as well. So for us, it means that this is going to be flipped. So the hole will be on the right, just because Abacus models X going to the right. So we're going to start with putting our center point that I always like to do, and we're going to fix that in place. And then I'm going to create my horizontal and vertical axes. All right, so let's start by creating our hole cross section, and then we'll just add in our outer sketch for the plate. Dimensions aren't as important right now, although it's kind of nice if you can draw your things out to try to auto constrain your lines as being vertical and horizontal. We'll go ahead and we'll set, since L is for both edges, we're going to make these two equal length. We'll apply our radius, which is 1. Then we'll apply our outer length, which is 4. And you'll note the entire geometry here is now green, and so we'll finish that. And again, I like to make my curve refinement X refine. Okay, so we've made our part. Next step is to go off into properties, and we'll just call this Hughes material since he's defined it. We'll create an elastic modulus, and from the problem it's 1e5, and the Poisson ratio is 0.3. Notice that for now I'm not going to create a density, but we'll come back to creating a density for our dynamic solvers. So as I kind of alluded to, we're going to do various kinds of solvers. So I'm going to go ahead and rename my module or my model right now, and I'm going to call this plate, and we'll go implicit static, so IS for that, and maybe mesh density 1x. And so it'll be clear why I've named this the way it is for now. Oops, misspelling here. Okay, we'll create our section. And so we're going to go ahead and create this model as Hughes and then we'll assign it to our geometry. Okay, we'll go into our assembly, we'll create the instance of the model, we'll go into our step module, we'll create a step for afterwards, and we'll just keep it as static general. Let's leave nonlinear geometry to off for this case. So again, we're in a linear finite element course, so we'll keep this in a linear setting. We'll touch nonlinear geometry though later in this course. And then we'll leave all these defaults as they are. Okay, now we're not going to have any interaction, so we're going to skip through this module. We'll go straight into our load section. Now again, he said we have symmetry on, I should go ahead and show this, we have symmetry on these two faces. And so here we have Y symmetry on the bottom, so let's go ahead and create this Y symmetry. Actually, let's go ahead and apply this in the initial load, not that it makes a difference, but for completeness. And let's maybe call this the Y center line. Or let's call this set just Y symmetry. And again, Y symmetry, so displacements in the Y direction, U2, are 0, and then rotations around X and around Z are also 0. We see our boundary conditions have been applied. We'll create our next one, which is X symmetry. On this section, call this X symmetry. Again, X symmetry because U1 is 0, and then our rotations are 0. Okay, now we'll apply our load. And again, he's mentioned here that the load Tx is pulling away from the hole, and also that it's an applied stress or an applied pressure that's uniform of value of 10, right? So that means for us, we need to go ahead and apply our load in step. It's a pressure. Let's call this Tx. And then we'll call this load surface. Select our surface here. And one of the things I want to point out is that so uniform value is 10. Now look at, there are going to be some arrows here that are going to help us see what's happening. So we set a value of 10 for pressure. Abacus defines a positive pressure to be into the surface that you've applied it to. So just know that that's counterintuitive, where here you might have thought that value of 10 should have been in the positive direction. But when you're applying pressure to a surface, it's independent of the coordinate system. It's just relative to the surface. So we can come in here and edit this and set this value to -10. And we'll see that our arrows have switched directions. Okay, now let's go ahead and go to our mesh and we'll modify the part. Now, first thing I want to point out is if we again recall our the mesh densities that were specified by Hughes, notice that we're not going to run this coarses mesh, although maybe I recommend that you do this yourself. But note that he starts with a mesh straight down the middle of this radius here, and then is refining within there. So there's one constant here, so it's really important that we get this, the ability of having our coarsest mesh looking like this. And so the way we're going to do that is by partitioning this surface. So I use the partition by face, or partition by sketch on a face, and then we'll draw a line. I'm just going to purposely make this look a little off kilter. Okay, so I've at least fixed it to this point up here, but I want this point to be bisecting this. So I'm going to choose a constraint where I can say that this is going to be, say, equal distance, in this case, between these two. There'd be other ways too that, and I'll just go ahead and show those, but this is one way to do a constraint on this circle. But if you weren't able to apply that, note that if I start up here, could have started anywhere, but as I drag this mouse along, at a certain point it kind of like snaps to a point, right? And it gives me a new icon. And that's again my auto selecting, or Abacus is auto applying a constraint, helping me out there. Alright. Now notice that the color of my mesh is pink, and that should signal to you that it's going to do an unstructured mesh layout. In many cases you don't want that. So again, here it said quad dominated. What that means, it would have allowed a triangle mesh. So we want to have a quad mesh, and we know that we can have a structured mesh here, so we're going to define to be structured. Now notice that if we were to set this approximate size to a large value, say like 4, which is this length here, the auto seed, if we mesh this, will be the linear finite element equivalent of what's been defined by Hughes. And notice how this is a linear facet representation of my circle. If I, and we can kind of see like the error to approximation of that circle. If we choose the assign element type to the region, you could choose be quadratic, and so part of the homework assignment is going to allow for you to look at changing the geometric order from a linear to a quadratic element. And if we do this, now Abacus is at least representing the nodes. It's still faceting in between, but this is actually a quadratic basis function. So even though it looks linear here, I'll show you a way in Abacus to, on post-processing, at least show you the actual geometry of the basis function. But for now, let's go ahead and reset this geometry to a linear. And you know, maybe one of the points to make out, but maybe not, is you'll probably not want to actually run this coarsest mesh definition. You'll probably want to start somewhere more like in mesh 2 or mesh 3 and do your refinement, but you certainly could start with this mesh 1. But here I'm going to at least start with mesh 2. And so a couple of different ways you can do this if you want is you can set a seed size by on each edge. And so we could come here and select these edges, which from Hughes we can see there are 2 elements along each of those edges. And so we could set those values either by size or by number. And so we could say I want to have 2 elements along each of those edges. But furthermore, there's this constraints. So once we set this to be 2, we want to tell Abacus, because we want to be very specific here with our mesh refinement study, tell it do not allow the number of elements to change. And so that can be difficult in some more complex geometries if you don't allow the elements to change. That if you've essentially set an incompatible seed constraint, then you will not be able to create a mesh potentially. And so it is kind of good to sometimes allow Abacus in practice to increase or decrease the elements, and usually by just a small little bit, to allow it to construct your mesh. So you really should only choose this if you're absolutely certain that you can construct a mesh with the chosen density, or you absolutely care about a single specific region that you want to fix the number of elements for. And then now what we're going to do is, if we look at, again, hues, he mentions we have 4 elements along this entire edge, but really it's 2 elements in this section and 2 elements in that section. And so we can come in here and select now each of these 2 edges. And again, by number, set the number to be 2, and then make sure our constraint is, again, do not allow them to change. And then we can go ahead and mesh this model. You can see that this then is the equivalent linear finite element basis or mesh to Hughes's mesh 2. And so if you wanted, maybe instead of saying mesh density 1x, maybe you want to change this to Hughes mesh 2 as a name. And then you could simply copy the models. We'll show that in a little bit, but you could then simply copy the models for each of the different densities. All right, so our model is fully set up. Actually, I should mention one more thing. We're not quite done. In the element type, notice that we haven't yet set really anywhere to be plane stress or plane strain. In the family, we'll see that this is where you would choose to either be a plane stress or a plane strain type element. So if I'd click this, I'd be a plane strain finite element. In this one, we're going to be a plane stress. I'm going to go ahead and turn off reduce integration so that we're fully integrated here. All right. Now with that, we're going to go ahead and create our job. So we'll go to our job manager, create a job, and I'm just going to give the job the same name as my model. And we're going to leave all these defaults the way they are. And we'll go ahead and we'll submit our model. And again, we can check the monitor, and we can make sure that we don't have any warnings or errors in there. Let's go see our results. Okay, if we click on this button here, we'll see our contours of our elements, and we'll see now we have stress, von Mises stress is being plotted. And a couple things in this viewport. I'm going to go ahead and change my legend here a little bit, just to get rid of a few, or clean up this a little bit. I'm going to turn off the bounding box. I'm going to leave set fixed. Well, maybe we'll do this. We'll do a scientific, but with 0 decimal places. And then I'm going to change the font of all these to 8, and see if we can apply this to every single one of those different annotations. Now, one thing you might be asking yourself is that you can actually kind of see that there's, well, let's go ahead and animate by scale factor. You can see if we go ahead and let this swing back and forth, maybe add a few more frames, say to 30 frames. You can see it looks like there's quite a bit of deformation here. And the reason why that looks at it is, notice down here it says deformation scale factor is 800. And so Abacus is trying to give you a feel for the mode of deformation, and so it's scaling all displacements. And so we can change that by coming up to common options, and you'll see that it's auto-computed to about 765. I usually like to at least make myself a uniform deformation of 1 to make sure, again, that my model physically makes sense, right? That I shouldn't be able to see any deformation in my model for this case. And then you can always flip back and forth between auto-computing if you want to see the mode of deflection, or back to your uniform. So for now, I'm actually going to leave this deformation scale factor on, but actually maybe I'm going to make it a little bit more uniform and just make it 1,000. Okay. So a couple of things that I want to point out just on this model. is kind of a neat way to do some post-processing. So one thing we're going to do is we're going to create a path. So if you come to Tools, Path Manager, we can create a path. We can give it an edge list, and we'll call this the whole. And so you'll see our part can be finite plate. If we had multiple parts in our assembly, we could choose different ones. And then we'll choose to select from viewport, add before. And now it doesn't really matter which direction you choose, but maybe we'll choose to select path moving from this place of highest stress down to 0. So I'm holding shift to select. It may not be needed. Also, you could have chosen feature edge, and so in that case, if you choose a feature, it should select stuff. I'm actually not sure what I've selected now. So it looks like you don't have to hold down shift select. And so then this would be the end node. Oh yeah, this doesn't seem to do it quite what I like. There should be a way to get that to work. But I guess for now I'll just select my edges manually. Okay. Now, again, the homework problem, or Hughes's problem, provides out analytic solutions in cylindrical coordinates, but he also provides, if you care, just the stress concentration in the x direction. So the XX, or 1,1 stress at the edge of that hole is 30. And so you can just, if you want, you can, instead of choosing von Mises to plot by, you could select S11. And again, that's in our global coordinate system that's defined the one direction to be x. And so this isn't too much help for us. But one of the things we can do is we can actually probe out that actual value that's there. So that's a... sorry. You're going to click on the Query Information icon and then Probe Values in the Visualization module. And so now what we'll have is we can probe different things. We can select by elements and at which positions. You can also probe nodes. And so, for instance, we could select this node and we can see the reported stress at that location is 24. And if you wanted to, you could write this to a file. And again, I would recommend that you look through the different options that you have. So, say integration points for a given element, and so forth. But now let's go ahead. Let's just finish off our path discussion. We can create XY data from our path. And if we had multiple paths, we could choose which path we wanted. We could also choose either deformed or undeformed state. I'm going to go ahead and choose the undeformed state because the analytic solution here, you'll note, doesn't prescribe anything about displacements. And so we're making like this small displacement assumption here. And then you can have, so what's going to be plotted on the x-axis is like, say, a true distance. And there are various different things that you could set here. Notice that field output variable is going to be S11 and this average 75%. We're going to talk about what that is, but if you wanted to change, you could go ahead and you could change what your components are from within here. And so over various different options. And if we go ahead and, and again, we could choose multiple points if we wanted to. And so then this would essentially subselect from within. Again, we have a linear facet here, so there's no real point in subselecting or interpolating inside of. So we'll just go ahead and say plot. And here we have our plot. We can see distance along the path. And we can see our stress values at S11 along that path. And then, as we mentioned also, if you would like to do some more advanced post processing, so in our case we happen to know what the coordinates are. We know we're a circle, and so you can compute out, this is essentially a length along the circumference, you can compute that out to like x and y positions or radial values. So if you wanted to, you could do that by to plug in tools, Excel utilities, and then we could, so our current XY plot, we can go ahead and output this. And then once you've output it to Excel, Excel's been really nice, or Abac has been nice and has created your Excel already with a plot created in it. And one of the things that is a bit annoying is it doesn't tell you it doesn't explicitly tell you what the titles or labels are for these directions, but again it plots or it outputs them by X and Y. So again, this would be X, Y as far as what's being on the axis of the plot, which as we know is true distance along path, and this is stress 1, 1. And so oftentimes when you're plotting, you might be outputting, say, 30 different values. You can just have, a whole bunch of columns that are filled up in Excel, and you just got to remember X, Y, X, Y, X, Y, X, Y. All right, but I'm going to close this for now. Let's kind of talk about where we're at. So we have done a single mesh analysis with linear quads on just the mesh 2. And part of this assignment, again, we're going to want to do refinement. So we're going to increase our density to, say, mesh 3. To note here that there are 4 elements along this edge and 1, 2, 3, 4 along each of these edges. So it's just a factor of 2. So I'm just going to copy this model and call this implicit static mesh 3. I'll come back to my meshing module. I'm on the part, and then I can go in here again, select my edges, and then I can change them to be number of elements 4, and then I'm going to select these edges around the hole and set them to be 4. And again, recreate my mesh, and then I don't have to do anything else because I've already got the rest of my models already been pre-populated from my copy. So I'm just going to create a new job and call this plate is mesh 3. And now this simulation is completed. So we'll go and look at the results on this one. And again, we'll just notice that our mesh should be, as our mesh is refining, we should get closer and closer values to that exact solution of 30. So we'll make sure to plot again S11, and then we can query by probing that value at this node. And again, we see we're starting to get pretty accurate results to that. And so you're going to be asked again in the assignment to run a mesh convergence study and then to talk about the convergence rate. And again, what I would recommend too is that this value here maybe has limited precision, but as you maybe I can show this here, that if we probe again this value, we could write this to a file, and we could choose our significant digits here. You notice that I had chosen the output. I think I should have enough, but it'll let you go up to 9. And it'll spit this out as a report file, but you might try to give this a unique name. So like implicit static mesh 3. And again, we would find that then in our Abacus temp directory, or if we'd chosen a different directory, it would show up there. You should be able to edit this within something like Notepad++. And again, we're limited in precision because we'd only asked for single precision on our output. And so if you wanted to change your precision, you could change your jobs for precision output to be full. And then we can probe this value. And then this should allow us to have additional significant digits. And so perhaps not. So maybe that's not as accurate, although it is possible that if we were to create our little probe or our path, and then create XY data from this path. And again, export as Excel. So you'll see now we have full precision on our output values in here if you select on a single one. So that might be useful if you're looking for increased precision on your mesh convergence study. Let's do an increased mesh density. So we'll do 4, and then we'll set again all of, and actually it ends up being that all of our edges have the, well, except for this internal edge, happen to have the same amount of elements along each. So if we mesh this one, we'll see 128 elements. We'll know, again, we know we're going to be good on nodes. But you can always, again, check your node count. But let's run with this one, or this mesh. And I'm just going to create a job. We won't look at the outputs on this. But let's go ahead and we'll run that job and we'll come back to it. So what I want to do now is let's take the opportunity to save. So maybe we call this plate structural mechanics. Let's copy this model and let's do I'm gonna kind of with some premonition here. We're gonna do implicit dynamic transient fidelity. So what does that mean? Well, if we go into our step, we'll see that we had previously chosen a static general. We can replace that step with dynamic implicit or implicit dynamic. And so again, we'll continue to choose nonlinear geometry to be off, but notice that in the application here, we can choose different applications, transient fidelity, moderate dissipation, quasi-static. If you have some questions of what those are, recall that again we can use context-sensitive help and click on it. And you're going to want to open this up actually in Edge or Internet Explorer. I'm going to use Edge. Okay, and now the documentation is up. You see all the different settings we could have chosen, but then we'll notice if we zoom in, if we can, you can see it's got some discussion on transient fidelity, and so certain things you might care about, all the way versus quasi-static. And so this kind of gives you more like a brief summary of what's going on. But typically there's oftentimes additional hyperlinks to take you into other sections. So I would encourage you to go and search through documentation and see if you can find the time integration techniques that are used by transient fidelity, moderate dissipation, and quasi-static. Okay, and so we're going to choose to run this simulation. But note, we'll see an error is going to crop up when we submit this job, and see if you can predict what that's going to be. But I'm just going to go ahead and give this a name, Mesh 4. Submit, and if I were to hit monitor, we'll notice an error is going to crop up here. And this error is that we haven't put in a material density. And so we can't, again, a dynamic simulation adds mass terms to our solver. And so without those mass terms, or a density, we can't actually add those mass terms. So to do that, we'll come back to our property. And then we will edit our hues property. Now, the problem definition doesn't ever specify what a density is. So we're just going to kind of throw in a term that seems reasonable, so maybe 1e minus 4. And then we'll go ahead and resubmit this job. And again, if we track the monitor, we should notice no errors or warnings on the input processing, and then our simulation is going to run. And one of the questions that's going to be asked in the assignment is to comment on like performance. And so just take a look at where's our previous implicit static job solved in a single step. We now notice that Abacus takes 88 steps to solve the problem. And we can also track the increments of each of these steps to be quite small. And so if we go to results and we say, look at this, and we can play time history, so we can kind of see like this simulation is like ringing down. And there's, we have swing mode on, which maybe we don't want to have, so we'll just say to loop. And if we were to plot, say, just our internal and external energies, so our internal energy and our kinetic energy, we can see our plot of internal energy here. We can see a lot of ringing that's going on. We'll talk about where that ringing comes from very next. So, or not quite next. Let's go back to, let's run another job. We'll copy this existing model, and we're going to at least create one that's moderate dissipation. So we'll edit our step. Application be moderate. And then we'll copy again, and we'll do one for quasi-static. And then lastly, we're going to create another one where we're going to do explicit dynamics. And so we'll replace the step here with dynamic explicit. Again, nonlinear geometry should be off. Now, note, when we run an explicit dynamics job, we'll need to modify the element formulation for the regions to be from the explicit library of elements. So we'll go ahead and we'll create a job. So we could create jobs for all those other ones that we'd run. So let's go ahead and at least create a few of these. So mesh 4. Note that there's a precision, single, and otherwise. I recommend that you just always set this to be double precision, just to remove quite a common cause of some issues. And so at least by switching to a double precision solver, we've eliminated the solver precision as a source of possible accuracy issues. I'm going to go ahead and create now jobs for the other jobs or other models that we'd create. Okay, so we've created jobs for each of those models. And notice if we again compare transient fidelity and the number of output times that it had, if we run the implicit dynamic quasi-static and we track its monitor, we'll see how many steps it's able to have. And so we'll see it solves in a single step, again as compared to our transient fidelity. We can run moderate dissipation. Again, we can track its monitor. And we see that it also solves in a single step. But if we run the explicit dynamics case, we'll notice something interesting about this solver. And so now notice the number of increments that the simulation is taking, as well as kind of, since we're going from time 0 to time 1 second, just the kind of essentially a proportion of how long it's taking to go along. So part of the assignment is going to ask you to comment on the scaling of an explicit dynamic simulation with respect to mesh density, or uniform mesh refinement. So what I would recommend doing is not to run multiple and different mesh densities, certainly at least not on some of the higher densities. This should be an algebraic term that you should be able to put together fairly easily once you talk about stable time steps in class. Now if we go and we look at the explicit dynamics result, we'll kind of notice again our simulation is kind of bouncing around a little bit. So it kind of looks maybe similar to what we saw with the transient fidelity. And I want to talk about that a little bit, about why we see that. So if we go to our load, we'll notice that we've applied an instantaneous amplitude to our model. Typically when you do explicit dynamics cases, if you're trying to actually get out a quasi-static response, you should use a smooth step amplitude. And so here we can set at time 0, our amplitude is 0, and at time maybe 0.75, our amplitude is 1. And then another quarter of the simulation to make sure that we've settled. And then we need to make sure that we choose that amplitude. And I'm going to go ahead and change our field output number of steps here to give ourselves, say, 100 time outputs. Let's go ahead and let's rerun the explicit dynamic simulation. The simulation is finished. Let's go ahead and look at our results. And now if we play through this time history, we'll see a much more gradual and kind of unimodal loading of our geometry. If we look at our ODB history output, And if we were to plot internal versus kinetic energies, we can essentially see the effect of the smooth application of the force as opposed to an instantaneous value and then letting stuff ring out. You can see that we kind of have loaded this up smoothly to our final step. And then we see no variation really in our internal energies. Something that's useful to point out is that oftentimes what we'll do is we'll compare internal energy to kinetic energy to verify that our simulation is static. And this is a case where essentially we can see our internal energy is just completely dwarfing our kinetic energy. We can change our plot to be a log scale on the x-axis. If we choose our axes options, we can choose for the y-axis to be log. And again, so on a log scale, we can see that our internal energy is multiple orders of magnitude larger, to our kinetic energy. Essentially, there is no kinetic energy in our model. And so we could say that this is now a static or quasi-static solution where, true, there is some kinetic energy going on in the model, but it's effectively, for all purposes here, 0. And we'll do another lecture later in this course that dives a little bit more into explicit versus implicit cases. Okay, so I want to just run through a few more things for folks. In your assignment, you're going to be asked to look at plotting a value. So just recall that we're plotting von Mises stress here, and there's this average 75%. So let's talk about that a little bit. If we look at our result options, we can see that we're plotting field output, but that we're averaging element output at the nodes. So recall from class where we talk about we have a C0 basis function, and recall that our solution variable is U, or displacement, and that strain is the derivative of our displacements. And then in our case, we have linear elasticity. Our constitutive model is essentially a proportional relationship of stress to strain. If we turn off averaging element output at nodes, we'll now see something that's a little bit different. And just note now that, again, we're plotting stress. Let's see, maybe even go to stress 1,1, and notice that we can see discontinuities in our stress field between elements. And then we could also choose to plot the discontinuities instead. And so now we're plotting the discontinuities of S11 on our elements. And so, again, the assignment is going to ask you to comment on these discontinuities that you're seeing, as well as if there's any change in the behavior due to mesh refinement. And then another thing that we're going to do in this assignment is look at quad versus tri meshes. And so let's go ahead and let's take our implicit static mesh 4, and now let's maybe call it with tri. Let's go to our mesh module, and let's assign now, instead of these quads, let's assign triangle mesh and structured. And so especially if we do structured, what we'll see is that we essentially have, you can kind of visualize the quads that are there. But this is effectively taking each quad and then turning them into equivalent triangles. And so this is what happens if you were to, say, choose a structured mesh. And we can talk about that maybe this isn't a fair comparison due to maybe variation in element density or element quality. So if we wanted to, we could instead choose to have a free mesh and then turn off mapped meshing. And we can see our mesh here. But we're going to go ahead and use the structured mesh that we defined. So let's take this. one of the things we could do is we could even verify, again, the mesh and the number of nodes, and we'll find that the number of nodes in this case should have been equal to the number of nodes we had in our quad case. So if we evaluate the quads, we'll see again, different number of elements, but still the same amount of nodes. So let's go back to our geometry, and we'll go ahead and make sure that, again, our element formulation is a linear triangle. So we're going to do linear tries here for this case. And then we'll create our job. So plate, implicit static, mesh 4, lin try. We can look at these results. And again, you're going to make sure that when you're doing these things that you're using some kind of consistent mode of plotting and getting out values. And so, again, we can query values by probing. So we'll probe this value here. And again, the assignment's going to ask for you to look at the convergence of the, whoops, that's Mises. We wanted this to be S11. It's going to ask you to look at the convergence of S11 with linear triangles. And then if you're able to use quadratics, you might try doing some sort of convergence study if you convert these linear triangles to quadratics. So just note again that I had chosen order quadratic try. Let's just use the default formulation. And we could create a new job . And look at these results. And now go ahead and do a mesh convergence study on quadratic tries. Okay, and there's only one more thing I want to show you. So let's go ahead and let's do that very coarsest model. The very coarsest mesh, I should say. So mesh 1. Let's make our mesh. And again, set these, all the edges except for the interior edge to have a number of 1. But let's go ahead and choose quadratics. And then let's run this simulation. Now we'll see, again, this is really too coarse of a mesh, but what I wanted to show is that under ODB display options, you could choose curved lines and faces refinement level to say be extra fine. And we'll see now, notice how our geometry now has actually got a very fine kind of curvature to it. So again, we're using isoparametric elements, and so our basis functions are quadratic, and so not only are our fields, our solutions mapped on quadratic bases, but also our geometry is using quadratic bases. And so now we're able to see that we have a closer approximation to that circle. So that's going to conclude this video lecture.